Hello and welcome to Ms. Ma's Advanced Functions class. This is 9.3, the products of functions. So we're going to be looking at some of the products of functions. We've already talked about some of the properties already. So we'll just jump into the examples right now. So example A, determine the graph, the domain, and the range of y equals fg of x given the graphs below. Then find fg of -1 and fg of -2. I'm going to just label these. This one's going to be f of x, and this one's going to be g of x. So we're going to use this information to graph. So the first thing that we notice is that the domain of f is going to be x in R such that x is less than equal to 1. And the domain of g is going to be x in R such that x is greater than equal to -2. So that tells us that the domain of f times g, just like the domain of f plus g and f minus g, will be x in R, so that it is in between these two. So I have to define it from here to here, because those are the two endpoints of our functions. So it goes from -2 to 1, like that, okay? So we just do that right away. It's pretty straightforward. fg of -1, so f of -1 is equal to, and I just look on the graph and you can see it's -4, and g of -1 is equal to 0. So fg of -1 will be -4 times 0, which is 0. Okay, so that's the value, and we can actually use that to graph it, so we're going to just draw that in there right here. I'm going to draw it in black, and if I want to find fg of -2, it's going to be f of -2, which is -3 times g of -2, which is -1, so the value is 3. Okay, that actually gives us one of the endpoints that we need. So we are going to just need a couple more values here, and then we can graph it for ourselves. So I actually do want to find the value of fg right here, so I'm going to take the x value, which is 0, times whatever this is. It doesn't matter, because 0 times anything is 0, so that's also going to be a 0. So you'll notice that if f is equal to 0, then fg will be equal to 0, and if g is equal to 0, then fg will also be equal to 0. So we get double the zeros, or however many zeros we have. We just add up the number of zeros, because they're going to be multiplying by 0, so it gives us zeros. This is probably about a third, and this is about -3, so I'm going to make that about -1. Like this, and then we're going to connect the dots in a curvy and attractive manner. So I think f of g is going to look something like this. Okay, and there we go. That's it. That's fg, and we can label it fg of x. So now we have found the domain, and we have found the graph. Now we can find the range, and of course we don't want to find the range until we've actually graphed it all out. If we think that it could go lower, then we might want to see if we could find a different point, but I think that we're pretty, I think that might end up being the lowest point. So we could do some checking and do a table of values if we had the algebraic expression, but we don't. So we're going to write the range. The range fg is about y in R such that -1 is the lowest. You can see it's right here, and the highest is 3. And there you go. So I have found my range. The domain is the easiest thing to find, and I've also found my graph. So that happens if you have a graph, you can find fg. Okay, so if we want to do it algebraically, let's try this question. Let f of x equal root x and g of x equal 1/2 x minus 2. So all we have to do is put those values in. So fg of x is root x times 1/2 x minus 2. And if we could, we would simplify that, but that's pretty simplified because we have a square root there. To determine fg of 4, we're just going to substitute 4 wherever we see x. So root 4 times 1/2 times 4 minus 2, which gives us 2 times 2 minus 2, which is 0. So that's fg of 4. And again, we're just substituting into that equation. Find the domain of y equals fg of x. So first we need to find the domain of f, which is x in R such that x is greater than equal to 0. It's the square root function. And the domain of g, because it's a line, it has no limitation, so x in R. So the intersection is only going to be limited by the domain of f. So the domain of fg is going to be x in R, such that x is greater than equal to 0. Okay? And the last question says, sketch a guess for the graph, then verify with graphing technology. There are a few things that we could do with this. We could find the zeros, which is wherever f is equal to 0 or g is equal to 0, or both. We could figure out what the y-intercept is by multiplying the y-intercepts together. So we do f of 0 times, we do fg of 0. Y-intercept is fg of 0. F of 0 times g of 0. So that's all we have to do for that. And if we have any endpoints, we'd want to know the values for that. So, you know, you can go ahead and do that. So why don't you try that on your own? And I'm going to, well, I have already done it, so pause the video and do it right now. Okay, so hopefully you did try it and you did pause the video. If I graph it on my graphing calculator, it looks like this. So hopefully you have something that looks something similar to this. It's stops at 0 as we predicted, and bends down. It has another 0 at 4. Hopefully you got that one. Of course, y-intercepts, it's going to end up being 0 since that is one of the zeros, but anyways, that's what it ends up looking like. Alright, one more. So the rate at which a contaminant leaves a storm sewer and enters a lake depends on two factors: concentration of the contaminant in the water from the sewer and the rate at which the water leaves the sewer. So both of these factors vary with time. Concentration of the contaminant in kilograms per cubic meters of water is given by C of t equals t squared, where t is in seconds. The rate at which the water leaves the sewer in cubic meters per second is given by W of t equals 1 over t to the 4 plus 20. Determine the time at which the contaminant leaves the sewer and enters the lake at the maximum rate. Okay, so C of t is given in kilograms per meters cubed, and W of t is given by meters cubed per second. So this is actually a really important thing to know, because we're not really sure if we should add or subtract or multiply these two terms together. And if we want to do the rate at which, the time at which the contaminant leaves the sewer and enters the lake at the maximum rate, so that means that we want to find a rate and we want to do it in time. So what we're going to be finding is, and if we multiply these together, we're going to get kilograms per meters cubed times meters cubed per second. If I wanted to do an adding or subtracting, I should find that I have the same units, right? But because I have different units, I'm going to have to multiply them together. You can see that the meters cubed are going to cancel out. So when I do C of t times W of t, this is going to end up being in kilograms per second. So we want to know what the maximum rate is for that. So we would do C of t times W of t. So C W of t is going to equal x squared, or t squared, I guess, sorry. T squared, oops, CW of t is equal to t squared times 1 over t to the 4 plus 20, which of course is t squared over t to the 4 plus 20. Now we might have a very difficult time finding this. The maximum rate is going to be where we do hit a maximum. We can use the instantaneous rate of change to find where the instantaneous rate of change is 0, and that will give us maximums and minimums. However, this is a very complicated one, so I just drew the graph for you. So we would want to just type this into our graphing calculator, and actually we're going to do that in class, and we're going to type this into our graphing calculator and use the graphing calculator to find the maximum, which ends up being at 0.11. So the time at which the contaminant leaves the sewer, enters lake at the maximum rate is at 2 seconds. But anyways, so this is a somewhat difficult question, because, and you know, just because of the units and things like that, it's very unclear what exactly they want us to do with it. But we do use a graphing calculator to solve it, so in the end it ends up being sort of on the simple side. Okay? So anyways, hope that you enjoyed the video. The basic concept is that we want to multiply the y values together in order to get the y value for fg. And we can find the domain by just finding the intersection of the two original domains. Okay? Oh, and one more thing. We do have x-intercepts wherever the originals have x-intercepts. So I hope you enjoyed it. Thanks for watching, and I'll see you soon. Bye!